Hello Internet, I'm Terrence and you are watching A Maker Dad. In this video, I'm going to go over the fabrication of the Pinewood Derby car tools that I've shared. Let's get started.
Beep boop, beep boop.
First, let's take a look at the materials used for 3D printing. Most beginners to 3D printing will start with PLA, or polylactic acid. PLA is often called a bioplastic. It is made from fermented plant starch such as corn or sugarcane. It tends to print with a pleasant odor with very little warping issues. However, PLA parts tend to be stiff and brittle and they will start deforming at a lower temperature. If you ever leave a PLA part in a hot car, it will deform. One step up from PLA is PETG, or polyethylene tetrafilate glycol-modified. This is very similar to the material used in drinks bottle. In fact, some advanced 3D printer folks make BPET or bottled PET from recycling drinks bottles. PETG parts tend to bend and flex instead of break, and can withstand higher temperatures before deforming. Unfortunately, PETG parts will also warp off the print bed, especially a large part on an unenclosed printer. In my garage, I run my printers in a heated, enclosed chamber to prevent warping and other issues when printing large PETG parts. Most of the parts that are presented can be printed in PLA. For the wheel chucks, PLA can work, but PETG will result in a chuck that can flex more and last longer. To change the material used, you can select different materials in PrusaSlicer to generate G-code for different printing materials. Simply come over to the panel on the right and select the material, then hit Slice to generate the new G-code. The track, bounding box, drill clamps, and axle drilling fixtures are pretty straightforward. Just slice the models and generate the G-code and feed it to the printer. One note, as a mechanical engineer printing often functional parts, my user settings lean towards building strong parts versus printing parts quickly. I typically generate parts with 4 or 5 parameters, which translates to about 2 millimeters of wall thickness of solid plastic. This is especially useful if I'm using heat stake inserts, which we aren't using here on this project. At home on my 3D printer setup, I am running Octoprint on a Raspberry Pi 4 with some custom I/O configured for lights and camera control. It also uses a Raspberry Pi camera for remote monitoring, so I can see whether my prints have degenerated into a plate of plastic spaghetti and stop the print from any web browser. To put the drill fixture together, thread an M8 nut onto the end of each threaded rod, then pull the rod up through the hole. Thread an M8 nut down on each rod end and repeat for the other 3 holes. Press an M8 nut into the hex opening and thread an M8 screw from the other side. Now, place the drill into the fixture, apply the clamping elements, and hold the front and back clamping elements together with more threaded rods. The base and height inserts for the balancing fixture is pretty straightforward, but the slider in the balancing fixture is printed with support material. Let's take a closer look at how this is done. If we were to apply supports everywhere, there will be supports generated on this dovetail surface of the slider, and we don't want that. So we tell PrusaSlicer to only place support material where the support enforcer is, and we add a block to the tip of the pointer. Now, this isn't going to be perfect. Let's slice the part and take a look layer by layer. You can see the support material built up here, and it provides a surface for the feature to bridge to, but there's still some unsupported material here above the dovetail surface, and we can expect this material to droop during printing. And sure enough, when the part is printed, we see a little bit of drooping on the back, which we can file off with a couple of passes with our plastic file. I am using a Tamiya plastic file. I found this to be a little less aggressive than a regular file for filing 3D printed plastics. Link in the description below. The inner and outer wheel chucks are oriented in this orientation to eliminate the need for support material. We actually went through a few design iterations on these wheel chucks. Originally, the shafts were round. There was a concern about the layer seam though. Where the printer starts and stops on the layer, inevitably there will be a slight raised burr. This is not necessarily obvious to the end user. They can chuck it on the burr and have the chuck be off-axis in the drill. To solve this, we went to a hexagonal shaft profile because we know that PrusaSlicer will always put the seam of the hexagon on the corner. By moving the seams to the corner, we can be sure that a user won't accidentally chuck it into a drill on the seam. There is a big stabilizing foot that's printed that will need to be removed from the print. This is another trick that you'll often see in 3D printing. To remove the foot, we use a pair of diagonal clippers and just clip it off. A few passes with a file to put the chamfered cut there eliminates any burrs. The chamfers don't have to be perfect, you just don't want a high point to interfere with the clamping of the chuck in the drill chuck. The inner chuck expander piece is printed with an encapsulated nut. We want the nut to be encapsulated as we will both be pushing and pulling on the expander piece with the screw. To do this, we insert a pause G-code command into the code. The slice pause but command is executed before the layer's code, so we'll put it at z equals 6.2 here, right when it starts to close off the hex opening for the nut to sit in. Note that if you're using Octoprint, you will also need to set the following G-code script in the configuration. Otherwise, the printer won't come back to temperature upon resume. Finally, to assemble the wheel chucks, on the external chuck, you want to insert a screwdriver or hex key into the helper hole to tighten the chuck. Don't rely on the drill chuck to hold it from spinning, as that will likely strip something out. For the inner chuck or the expanding mandrel setup, simply thread in the screw from the back to the expander piece. To get it to release, loosen the screw and tap the screw head on the table. This will cause the table to unjam and release the expanding mandrel. Finally, let's take a quick look at the axle drilling fixtures. We need to seat some M3 hex nuts into these hex openings, and to do that, we'll press in an M3 nut, then we'll use a screw to pull the nut all the way down, and then we'll unthread the screw. I am using an M3 by 20mm socket head cap screw here. We'll also chase the holes out by drilling them through with an 1/8" drill bit. Finally, assemble the entire drill fixture like this. Okay, let's talk a little bit about the fixtures and how we use them. Start by laying out the wheels. If you're moving the wheels to the extreme ends of the block, just line the fixture up to the edge of the block like this. If you need to move the wheels but maintain the wheelbase, you can scribe lines into the wood block, then line the V-notch in the drilling fixture with the line drawn. While we are laying out the block, we will also lay out the shape of the car. My son has drawn the shape of a car earlier on in a 1-to-1 CAD-generated printout of the block with the wheels at the extreme ends. I've made a few copies of it, and we cut one out and use it to trace the profile onto the car. These fixtures are kind of touchy. You want to remove the plastic collar from the drill bit that you're using, insert it into the fixture but not have the drill poke through the fixture. Then, start the drill, push it in and out while holding the drill trigger down. Do not let the drill stop in the wood or you will break a drill bit. We'd want to drill all the holes with a tungsten weight while the block is still a block shape. It'll make it a lot easier. Here, we drilled our rear tungsten weight holes, and then we used the fixture to drill the adjustable tungsten weight holes from the back. Next, we shaped the block. Again, order of operations matter here. Don't do what I did. I cut the side out, only to realize I've also cut off my markings on the block for the second operation. Oops. I ended up eyeballing the other cuts based on my first cut. While I'm helping my son on the bandsaw with cutting the block, he is polishing the axles. I want to point out his technique here for lathe filing. It doesn't matter as much on a drill, as drill chucks are pretty smooth, but if you're ever filing on a lathe with an exposed 3-jaw chuck, what he's doing here is the proper holding technique for filing on the lathe. The lathe chuck spins towards you, and he's holding the file lightly on the back side of the lathe, so if a draw ever catches the file flies away from him instead of towards him and into him. He's also holding it lightly with his fingers in such a way that the file can fly out of his fingers without going through his hand. Now, in my 20+ years of lathing things, I've never caught a file on a lathe chuck. But these safety rules are there to ensure that I don't get skewered by a file if I ever do. Okay, so back to the pine car. The block is shaped, so we give it a few coats of paint. The Rebel Alliance logo here actually gave us quite a bit of grief. I can talk about more of that in a later video. We found that the paint can add a pretty significant amount of weight to the block, so now we fully paint the block before tuning the final weight. After the paint had dried, we then put all the components of the car onto a scale down to the last screw and nail. We then add tungsten weights to get the final weight to 5 ounces. We'll glue the weights in with CA glue, and then we'll drive the nails in with the wheels. Next, we balance the car. Using the height adjustable inserts, we pick the insert that just lifts the car off the ground. In our case, because the car is a little bit front heavy, the best we can do is to get the center of gravity to be about 27 millimeters in front of the rear axle. Normally we would aim for 20 millimeters, but there's enough weight in the front of the car that it didn't happen this year. Finally, we check the car against the sample racetrack in the bounding box and re-verify the weight to make sure that we are within the weight limit. Everything looks good, so it's off to turn the car in. For all the scouts watching this video, do your best and have fun. I want to thank you all for watching. If you like what you see, please like, subscribe, and feel free to leave me a comment. That will really help me get this channel off the ground. Okay, that's it for this video. I'll see you next time. Bye!